In this video, we will talk about differentiation rules. We will write down different rules for the derivatives that we can use to compute the derivative of different functions without going into the limit definition of the derivative. So let's write down differentiation rules. The first one is for constant functions. One, constant function. So suppose if our function f of x equals to any constant, c is a constant, then the derivative of this function would be equal to 0. Any constant. We'll see a brief proof as well. For example, suppose our f of x equals 10, or f of x equals negative 100, or f of x equals sine of 10. All these are constant numbers. In each case, the derivative of f with respect to x would be equal to 0. Let's look at a brief proof of this. Where are these rules coming from? We might give up the proof soon, but for this one we can do. The derivative of f, when f is a constant function, equals, by definition, limit h approaching to 0, f of a plus h minus f of a divided by h. But you see, our function is constant. F of a plus h is going to be c. F of a is also going to be equal to c. This gives me limit h going to 0, c minus c divided by h. That comes out as 0. C minus c is 0. The derivative of this function comes out as 0. Now we don't have to do this limit definition every time we take the derivative of a constant function. As soon as we know the function is constant, we would write that its derivative with respect to x is equal to 0. Moving on, the second rule is for constant multiples. Derivative of a constant multiple. Suppose we are taking the derivative, suppose u of x is a differentiable function and k is a constant value, a real number. Then the rule says the derivative d over dx of k multiplied with u of x equals, you can pull out the k and take the derivative of the function u of x. Or another notation, you can write k du dx, the derivative of u with respect to x, or we can write k times u prime x. A constant that is multiplied with the function can come out of the derivative. That's what we mean here. Example, or maybe we'll get to the example in a minute. Before that, I'm going to look at the brief proof of this and write one more rule, and then we'll come back to that. So a proof. I want to find what is the derivative of this function, k times u of x. By definition, that would be equal to limit h approaching to 0, k times u x plus h, k is a constant, minus k u of x divided by h. I'm doing the derivative in general. Now you can see we can factor out this k from every term and out of the limit as well. It's k limit h approaching to 0, u of x plus h minus u of x divided by h. This guy here is the derivative of u by the limit definition. So this equals k d dx, the derivative with respect to x of the function u of x. Or in other words, k multiplied by u prime of x in any notation. Okay. Next one is the power rule. Three, the power rule. This rule says if n is any real number, and our function f of x equals x to the power n. The function is of this type. Then the rule says the derivative of f with respect to x, or f prime of x, that equals, you bring n down and you subtract 1 from the power. N times x to the power n minus 1. This is the derivative of x to the power n. For example, suppose my function is f of x equals x to the power 3. Then the derivative of this f with respect to x, which is the derivative of x cubed, it's all notation at this moment, the derivative with respect to x of x cubed, that would equal, by this rule, I would bring this 3 down and I would subtract 1 from 3. This becomes 3 x to the power 2. This is the derivative of x cubed with respect to x. Another example. Suppose our function now is x to the power 3 over 2. Then the derivative of this function g with respect to x, which is the derivative of x to the power 3 over 2, would be equal to, I will bring the power at front, 3 over 2, and then subtract 1 from it, minus 1. 3 over 2 minus 1 is 1 over 2. This becomes 3 divided by 2, x to the power 1 over 2. Or we can write 3 over 2, x under the root, in either form. Another example. Suppose now my function, let's call it u of x, equals 1 over x to the power 4 over 3. 4 over 3 is in the exponent of x. And I want to take the derivative of u. We can still do it. Although it's not directly a function x to some exponent. X is in the denominator this time. But we might have to rewrite this function a little bit. Du dx, which is the derivative of 1 over x 4 over 3. First I rewrite this as d over dx, x to the power negative 4 over 3. Now our x is in the numerator. It's only one term, x with some exponent. We can take the derivative of this. We can bring the power at front, negative 4 over 3, and we subtract 1 from the power. Now we simplify the power. This is negative 4 over 3, x to the power negative 7 over 3. Negative 4 over 3, negative 1 is negative 7 over 3. Finally, I can write or du dx equals negative 4 divided by 3 x to the power plus 7 over 3. So although in this case the function here was not directly a function of the type x to an exponent, but we can still rewrite it and apply the formula. Now let's do an example on the constant multiples. We have written the rule already. Suppose now our function, let's write the function first, f of x equals 3x squared. 3 is multiplied with x squared, and we are taking the derivative of this. The derivative of f with respect to x equals the derivative with respect to x of 3x squared. Now, because 3 is multiplied with x squared, it's a multiplicative constant, I can factor this out or bring it out of the derivative. I can write 3 d over dx of x squared. I know how to take the derivative of x squared. I'll bring 2 down and subtract 1 from the power. 3, 2 comes at front, x, 2 minus 1. Finally, we can write the derivative of f with respect to x equals 6 x to the power 1. Okay. So now we can deal with x to some exponent terms. Even if a constant is multiplied with such a term, we can deal with it. Let's extend this a little bit more. Let's state another rule. We wrote 3, that's the fourth one now. Derivative sum rule. Let's state the rule. If u and v are differentiable functions of the variable x, then the rule says the derivative with respect to x of u plus v, that equals the derivative of u with respect to x plus the derivative of v with respect to x. And remember, u and v are differentiable functions. We are assuming that. That's great. What we can do now is take the derivatives of these kind of functions. For example, suppose our f of x now is x cubed plus 4x plus 2. And I want to take the derivative of this. We can apply almost all of the rules that we just wrote. The derivative of f with respect to x, which is the derivative of these three terms, x cubed plus 4x plus 2. Now using this rule, which says the derivative of the sum is the sum of the derivatives, I can actually take the derivative of every term separately. I will write, using this fourth rule, I'm using rule 4, d over dx of x cubed, d over dx of 4x, plus the derivative of this constant term 2. Now, on the first term, I will apply the power rule. On the second term, I would first apply the constant multiple rule. And on the third term is the derivative of a constant. This equals, from the first term I bring 3 down and subtract 1 from the power, from the exponent. I write this as 4 d over dx of x first, plus the derivative of 2. 2 is a constant, the derivative of this would be 0. The first rule that we wrote. That equals 3 x to the 2 plus 4, the derivative of x. Let's do it separately here. It's a good thing to remember. The derivative of the x term. This derivative is always equal to 1. And I'll show you this by using the limit definition. We can always use it as a rule. The derivative of x with respect to x is always 1. That equals, if I apply the limit definition, limit h going to 0, my function is x. I am doing the derivative for f of x equals x. It's x plus h minus f of x divided by h. In that case, I get limit h going to 0. F of x plus h, when f equals x, is x plus h. F of x is x divided by h. These two cancel out. I get limit h going to 0, h divided by h itself. That's exactly 1. You can also use the power rule. Because the exponent on x is only 1. You bring 1 down and you subtract 1 from the power. It's 1 minus 1, which is x to the power 0. You'll get the derivative of x equal to 1. So now we can make it as a rule. d over dx of x is always equal to 1. I'm going to use that here. The derivative of x is 1. We are finally left with 3x squared plus 4. That's great. Now we can take the derivative of many different functions, combinations of different functions. I'm going to do one more example. Suppose my g of x now equals root x plus 7 over x squared. The derivative of g with respect to x would be equal to the derivative of root x, which is x to the 1 over 2. I will rewrite the second term as 7 x to the negative 2. Now I take the derivative of every term separately. x1 over 2 plus the derivative with respect to x of 7 x to the negative 2. Okay. That equals 1 over 2 x to the 1 over 2 minus 1. 7 comes out, and I write the derivative of x to the negative 2. This becomes 1 over 2 x to the negative 1 half, half minus 1, plus 7. Exponent comes down, and we subtract 1 from the exponent, which is x to the negative 3. In the end, I can write 1 over 2 x to the plus 1 over 2, which becomes square root of x, negative 14 divided by x to the plus 3. This is dg dx, or we can call it g prime of x. All right. Wonderful. The derivative, the next one is the derivative, next rule, the derivative of exponential function. Let's write this down. For the exponential function f of x equals e to the x, the derivative of f with respect to x, which is f prime of x, that equals e to the x is e to the x. The derivative of e to the x is the same function back. When the base is a different number, for example 2, 4, 6, or any other number, positive number, and when the exponent is different than x, for example 2x or x squared or any other function of x, we will modify that rule, but that's later on when we know the chain rule. It's going to come in the coming sections. Right now we have a specific form of the exponential functions. The base is e, the exponent is x, the derivative of e to the x in that case is e to the x back. For example, let's create an example here. Suppose our function v of x equals cube root of x negative 5 e to the x. And I want to take the derivative of this. dv dx, the derivative of v with respect to x, or v prime x, that would be equal to the derivative cube root of x negative 5 e to the x. Doing the derivative term by term, the derivative of cube root of x, I'm going to write it as x to the power 1 over 3, negative the derivative 5 e to the x. For the first term, we get 1 over 3. We bring it down. 1 over 3 minus 1, negative 5, the derivative of e to the x. This equals 1 over 3 x to the power 1 over 3 minus 1 is negative 2 over 3. Negative 5, the derivative of e to the x is e to the x itself. I can finally write v prime of x equals 1 over 3 x to the 2 over 3 negative 5 e to the x. That's great. Let's move on. Let's state another rule. Very useful one. We have done 5, so this is 6 of them. The product rule. This rule says if u and v are differentiable, then the derivative of u multiplied with v, these two functions are multiplied together, and they're not constants, they depend on x. By the product rule, it equals u multiplied with the derivative of v with respect to x plus the derivative of u with respect to x, and then this is multiplied with v of x. You take the derivative of one of the functions at the time, and then you multiply it with the other function, with a plus sign in the middle. For example, this is very useful. Suppose we are taking the derivative of, find the derivative of the function x squared e to the x plus 2 over x. Okay, when we find the derivative, we start with the derivative d over dx, x squared e to the x plus 2 divided by x. First, I take the derivative of every term separately. X squared e to the x plus the derivative of 2x to the negative 1. I'm going to rewrite it in this way. Now, the product rule applies on the first term, where x squared is multiplied with e to the x. So we apply the product rule on the first term. It would be x squared. I don't take the derivative of x squared, but I put the derivative on e to the x. Then plus, I take the derivative of x squared, but I don't take the derivative of e to the x then. Plus, for the second term, 2 comes out, and I take the derivative of x to the negative 1. Now we take the derivatives. X squared, the derivative of e to the x is e to the x. The derivative of x squared is 2x. It's multiplied with e to the x. Plus 2, negative 1 comes down, and we subtract 1 from the exponent. Power rule for x to the negative 1, just like x squared. Now let's simplify. From the first two terms, you can see I can factor out x, e to the x. I'll be left with x plus 2. And then from here I get negative 2x to the power negative 2. Finally, we can write this equals x e to the x, x plus 2, negative 2 divided by x to the plus 2. Wonderful. That was great. We can deal with a much bigger class of functions now. The functions can be multiplied together. We can throw in exponential functions as well. We can have any exponent on x. We can add these functions together. We can subtract them. That's great. That increases our ability to deal with a wide range of functions. Now another one. Throwing in another rule. That was 6, I think. Yeah. Now the 7. This is called the quotient rule. Okay. If u and v are differentiable, Then, wherever at any x value where v is not equal to 0, we have d over dx u divided by v equals v. I don't take the derivative of this. I multiply it with the derivative of u with respect to x. And then negative. Now there's a specific order. Negative. I don't take the derivative of u and I multiply it with the derivative of x. All divided by the square of v. And you can now see why this condition v not equal to 0 is coming in. We are dividing by the square of v. So first, it has to go that way. V, then the derivative of u, minus u, then the derivative of v. We cannot reverse the order of the terms. It doesn't matter for the product rule which term you do first. U dv dx or v du dx. But here we have a specific order. For example, we take the derivative of, compute the derivative of x divided by 2x plus 1. We have done the derivative of this by applying the limit definition. But now we're going to apply the quotient rule. No limit here. Okay, let's do that. The derivative of x divided by 2x plus 1. Anywhere where x is not equal to negative 1/2, the derivative would apply. My u is the numerator. This is u of x. And this guy in the denominator is our v of x. The denominator is squared. So 2x plus 1 squared in the formula. Then first we write our v, the denominator, and we do not take its derivative, but we do take the derivative of the numerator, which is x in this case. Then negative, we do not take the derivative of the numerator, but we multiply it with the derivative of the denominator. What we did at this stage, we only wrote out the quotient rule for u equals to x and v equals to 2x plus 1. Now let's take the derivatives. This is 2x plus 1. The derivative of x is 1. Negative x. The derivative of 2x plus 1 is the derivative of 2x plus the derivative of 1. I'll soon give up writing out the derivative of every term. We'll try to do them directly. But for now we can go like that. 2x plus 1 multiplied by 1. This is 2x plus 1. Negative x. The derivative of 2x, 2 comes out, and the derivative of x is 1. It would be 2 times 1. And the derivative of 1 is 0. All divided by 2x plus 1 whole squared. Simplifying, 2x plus 1 negative 2 times x, so negative 2x, all divided by 2x plus 1 squared. These two cancel out, and we are left with 1 divided by 2x plus 1 whole squared. That is exactly the derivative that we found when we applied the limit definition. Nice. The next topic is higher order derivatives. Higher order derivatives. That means we know the first derivative, then we take the second derivative, third derivative, fourth derivative, and so on. Let's write them down first. In general, we define the second derivative of y equals to f of x as f, notation is double prime now because it's the second derivative. The notation for that is, another notation is d2f divided by dx 3. My bad. dx2 is the second derivative. So d2f by dx to the power 2, that means the second derivative of f with respect to x. The way we find this is, we take the derivative of the first derivative of f. Similarly, the third derivative of f, in another notation, is d3f dx cubed. This is the derivative of the second derivative of f. Fourth derivative, I'm going to stop putting the bars. You see I have put round brackets around 4. When you see an exponent with round brackets on it, that usually means the number of derivatives. So this is the fourth derivative of f with respect to x. In this notation, it's still the same, d4f dx to the power 4. That equals the derivative with respect to x of the third derivative of f, and so on. And so on. For example, find or compute the third derivative of the function f of x equals x cubed negative 3x squared plus 2 plus e to the x. All right. The first derivative is the derivative with respect to x of the expression x cubed negative 3x squared plus 2 plus e to the x. I'm going to try to do things directly. The derivative of the first term is x cubed, would be 3x squared. The derivative of negative 3x squared is negative 6x. You bring 2 down, it gets multiplied with 3, and you subtract 1 from the power. The derivative of 2 would be 0, and the derivative of e to the x is e to the x. Now I take the second derivative. This implies the second derivative is the derivative of the first derivative. And my first derivative is 3x squared negative 6x plus e to the x. Again, I'll do it directly. The derivative of 3x squared would be 6x, because you bring 2 down and it gets multiplied with 3. You also subtract 1 from the exponent. The derivative of 6x, there's a negative sign as well. 6 comes out, and then you take the derivative of only x with respect to x. That is 1. Negative 6 multiplied by 1 plus the derivative of e to the x. This is e to the x. Now I take the third derivative. f triple prime is the derivative of the second derivative. This equals d over dx, 6x negative 6 plus e to the x. In a similar way, the derivative of 6x would be equal to 6. The derivative of negative 6 would be 0, plus the derivative of e to the x is e to the x. We can write the third derivative that we were looking for is 6 plus e to the x. And that's what we wanted. All right. Let's write another example. Now just apply the rules on it. Example, which asks, does the curve y equals x to the 4 negative 2x squared plus 2 have any horizontal tangents? And if it has, let's try to find those. Now, the slope of the tangent line comes from the derivative. And we want to find horizontal tangents. That means we want to find the tangent lines that have zero slope. So what I'll do is, I'll take the derivative of this given curve so that I have a general expression for the slope of the tangent line. For the slope of the tangent line, we take dy dx, which would be equal to the derivative of x to the 4 negative 2x squared plus 2. The derivative of the first term, this implies dy dx is 4x to the 3 negative 4x plus the derivative of 2 is 0. This is the slope of the tangent line at a general x value of this polynomial that defines the given curve. Now, because we want horizontal tangents, so for us the slope of the tangent line must be 0. So I force this to be equal to 0 for horizontal tangents dy dx must be equal to 0. This is only possible when 4x cubed negative 4x equals 0. We can factor that. Factoring out 4x, I get x squared minus 1 equals to 0. This implies x equals to 0. X squared minus 1 gives me x equals to negative 1 and x equals to plus 1. So we can write y equals 4, now x to the 4, negative 2x squared plus 2 has horizontal tangents when x equals 0 or x equals negative 1 or x equals to plus 1. We can also find these points. We can find these points explicitly. If I take x equals to 0, for example, x equals to 0 in the original curve gives y equals to plus 2. So the point is 0, 2. Similarly, when x is negative 1, y would be equal to negative 1 to the 4, negative 2 times negative 1 squared plus 2. That gives us 1, negative 2 plus 2, they cross out, equals to 1. Point is on the curve, negative 1, comma 1. And similarly, when x equals plus 1, we get y equals 1 to the 4, negative 2, 1 to the 2, plus 2. These two cancel out, and I get 1 again. The point is 1, comma 1. The curve will have horizontal tangents at negative 1, comma 1, 0, comma 2, and 1, comma 1. Okay, let's stop over here. We'll continue next time.